All right, so we just talked about polarization, which does not necessarily mean an object is charged, but only that there's a separation between its negative and positive charges. Um, Now let's talk about actually charging objects. We've already had to reference this quite a bit. So there are a few different ways, or a couple different ways to charge an object, and this depends on whether it's an insulator or a conductor. So let's start with insulators. Of course, this works with conductors as well, but the first means of trying to charge an object is through friction. So we already discussed this. So if you rub two objects together, depending on their electronegativity, which is not something we'll get into, one object will pull electrons off of the other, leaving both charged, right? So if I have two neutral objects and I rub them together, and object A pulls electrons off of object B, that'll make object A negative because it pulled the electrons off, and object B will be left positive because it lost electrons. Yes, so again, some examples of that are you could use stroking a cat's hair, combing your own hair, rubbing your shoes or socks on the carpet. These are all means of charging up through friction. Now, if I just put my sock on the carpet and leave it there, it's not going to necessarily charge. I need that friction in order to pull the charges off. Because again, in an insulator, electrons do not flow freely. So just touching a sock to carpet is not going to pull electrons off. The friction is necessary for that. But now conductors can be charged through two different means. One is called charging through conduction, and the other one's called charging through induction. So first we'll look at conduction. And just like with friction, conduction involves touch. So if you take a positive, essentially when you touch two conductors together, charges will spread evenly through them. So if I have two spheres, two metallic spheres. If sphere A has 10 coulombs of charge on it, and sphere B is initially neutral, and I bring them into contact, let me rephrase that. Let's say that, so we have two spheres, sphere A and B. Sphere B is completely neutral. Sphere A has negative 10 coulombs, meaning it has excess electrons. It has more electrons than it has positive charges, and the charges of those excess electrons adds up to negative 10 coulombs. Now, when I bring those two spheres in contact, what's going to happen? Well, we know that those excess electrons in sphere A are going to want to be as far as possible from each other, right? They're going to repel each other. So in sphere A, they're going to be stuck on the surface. Now, as soon as I bring sphere A in contact with the sphere B, they're going to distribute between sphere A and B. And then when I split up those two spheres, I pull them apart, they'll both be left with some excess charge. How much? Well, if it's the same type of metal, the same size spheres, they'll both have negative 5 coulombs. So the initial had negative 10, and then after they've come in contact, they'll each have negative 5. If one of the spheres was smaller than the other, or made out of a different material, that'll change how the charges are distributed, but they will still move through both. So conduction is charging through touch, right? And you don't need friction because these metallic spheres are conductive. Electrons can freely and easily move through them. We don't need that friction to take the electrons from one to the other. They want to get as far away from each other as possible, and so they'll push into this other conductor. And we can see an example of this animation here. So we see that this negatively charged rod, as it is brought closer to this neutral ball, it attracts the ball towards it, right? So, and as it's being attracted, we also see the ball being polarized. But the key point is once they're in contact, once these two conductors are touching, electrons flow into the conductive sphere. And then why does that sphere push away? Well, because now they're both overall negative, so they're going to repel each other. So another example of this could be say you're walking around on carpet with socks, and as you walk you drag your feet, so you get charged up through friction initially, right? So the socks pull charges off the carpet, and that goes into your body. Then you reach for a doorknob. As soon as you touch that doorknob, that charge can discharge into the doorknob, right? Again, that is through conduction. The key here, something I think I missed, is that the human body is conductive. We are very conductive, and that's why current can run through us. Yeah, so, yeah. Now let's look at the other means of charging, and that is charging through induction. So there's a couple ways to do this, but let me try to explain one. So say we have a charged object, like that charged rod that we keep bringing up, and again, some other neutral conductor, maybe some neutral metallic sphere. If you bring the charged object near the conductor will polarize, as we've seen, meaning the electrons will be forced to move to the surface of the material that's farthest away from the charged object. Now, if you tap that conductor, that sphere, you're essentially grounding it. So you can either tap it or touch it with an actual ground. And what that does is it allows charge to flow between the conductor and yourself, or the ground, whatever it is that's touching it. And that leaves that will leave the conductor charged once you've let go and removed the ground. Now the charge that it has depends on the charge of your charged object. So let's think about this again. If I have a negatively charged rod and I bring it near but not touching a spherical conductor, the negatively charged rod will push the electrons to the opposite side of the sphere. So the positive charges will be close to the negative rod, and the negative charges will be farther away. Now, when I tap that sphere, that rod, the negative of the rod is still trying to push the electrons in the sphere as far away as possible. It's repelling them. So as soon as I tap the sphere or touch it with the ground, the electrons have somewhere to go, somewhere farther from that negative rod, and so they'll ground through my body, and then when I let go, well, what's left behind? We've left these positive charges behind, and thus leaving it positively charged. If instead we use a positively charged rod, we bring that near the conductor, it'll pull electrons towards it, so near the positively charged rod, leaving positive charges on the opposite side of the sphere. And then when I touch the sphere, the conductor, this time the rod will pull electrons from me into the sphere. And thus, once I move the charged rod and myself away, the charges redistribute throughout the conductor, and since it pulled electrons out of me, it now has more electrons than it has protons, or positive charges, and therefore is now negatively charged. Another way to charge something by induction is by using two conductors, and you may notice this is essentially the same, right? So where in the previous example we used myself or some ground, here the ground is just a different conductor. So say you have two metal spheres, sphere A and B, and say that they're touching. So they're in contact. Let me just play the video. So as we bring this negatively charged rod near the spheres, it pushes electrons away from where the rod is. In this case, it pushes them into sphere B, since the rod is close to sphere A. Now, if we separate the spheres and then afterwards move this charged rod away, we'll have two charged spheres. Sphere B will be negative because it has more negative charges. Sphere A will be positive since it lost negative charges. Again, this is charging through induction. So I'll show you that video one more time. All right. One more example of induction. So it turns out that clouds are often polarized, and not because of some other charged object nearby. Rather, there's some complicated process within the cloud that has to do with the differences in temperature within the cloud and something similar to frictional charging that occurs in the cloud. And this causes the top of a cloud to be positively charged and the bottom of a cloud to be negatively charged. And remember, clouds can be quite large and they can hold a lot of charge. Now, this cloud sitting above some city will cause that city to have an induced positive charge. In other words, the surface of the Earth right below the negative cloud will have an induced positive charge. That's because the negatives of the cloud are pushing the negatives on the surface of the Earth there away, deep into the Earth, leaving the surface positive. Think about the Earth as an infinite pool of charge. So we pretty much will never say that the Earth has a charge. Because it's just so large. So when we say we're grounding something, that means we're taking charges away and generally just dumping it into the Earth, this giant pool of excess charge. And so here, the city, or the surface of the Earth, the cloud repels electrons on the surface of the Earth, leaving this surface region positively charged. Now, if this charge can build up enough, it can actually lead to a lightning strike, right? So the as we'll discuss in a moment, the electric field between the negatively charged cloud and the positively charged surface of the Earth gets so strong that it essentially creates this momentary vacuum in between the cloud and the surface of the Earth, and this vacuum has zero resistance. And that allows current to flow. So essentially, the cloud discharges through this lightning bolt into the Earth. All right, I'm gonna stop this video, and we'll finish up with one more video.